All right, kids. Well, you've made it to the last lesson of Algebra 2, and what we're going to do is some application of exponential and logarithmic concepts. First thing I want to do is make sure that you're comfortable with some of these main formulas that we're going to be working with. Don't forget about the exponential model, V equals C, 1 plus or minus r to the t. And it's always used for percent, right? It's always used for percent growth and decay. How about the compounding interest? Have we seen this one yet? I don't know if we have, but it's basically a variation of the exponential model, but we end up with some extra sort of parts, namely the letter n. If you're wondering what is the letter n, it just represents the number of compounds in a year. Typically, because we do things monthly, n is going to be 12. Don't worry, I'll show you how to work this out. But once again, we basically have like an exponent. We also have a base. The base is what's in parentheses. Compounding interest, that's basically when your money, you deposit some money and it starts to grow by a percentage. And then there's continuous compounding. This is kind of a special case of money growing literally continuously. Money is in like a continuous state of change. Now, I'll share with you that it's more in theory your money would grow this way, so that we can work with the letter E. Because remember, the letter E is like the natural or the continuous number. Now, again, if you haven't seen this formula, that's fine. We're going to figure out how to use it with some applications as well as each of these formulas. So let's take a look at this first problem where we're going to be trying to find T. In other words, we're going to be trying to find the time, which is going to be an exponent. How do we find exponents? Ding, ding, that's right, using logarithms. But hold on, we're a little bit ahead of ourselves here. First, let's just look at the problem. 20 bacteria on a certain rotting specimen, oh, that sounds lovely, are growing by 40% every hour. There it is, it's a percent change. Because this is a percent change, and it's not dealing with any type of specific money, we can basically say that we're going to be using the exponential model. Now, since you're growing by 40%, we're going to have a plus sign here. And what we can do is we can start to fill in so that we can figure out how long it takes until there's 211 bacteria. Now, kids, 211, that's like your final value. So keep in mind that that's what goes on the left side of the equal sign. That's always the final value. But we started with 20 bacteria, so that's what's going to show up on the that's what's going to get filled in as my initial value. Now, as I continue to put parts into this formula, we get to the spot where we have the rate. The rate is the percent as a decimal. Remember, you want to move the decimal 2 places. So we end up with the equation 211 equals 20, 1 plus 0.40 to the t. Now, kids, this equation we're going to be solving for the exponent, but before I get too fancy solving for the exponent, there's some things that I can do. The first thing would be simply to actually add 1 plus 0.4. So we get 1.4. Now, remember, we're solving this thing for t, so anytime you're solving for t or solving an equation, we want to kind of do inverse operations. And it's very important here that I try to isolate first by dealing with what's on the outside. So I divide by 20, and that's going to give me, use a calculator, that's going to give me 10.55. Now, at this point, I am at the key step to this problem. The key step, of course, is to solve for the exponent. And how do you solve for exponents? That's right, you slap both sides with a log. So I'm literally going to take the log of both sides. Now, what that does is it causes my exponent of t to come tumbling down. And I end up with kind of this little in-between step where I have t times the log of 1.4. Now, I'm still solving an equation, so I still have to do the business of inverse operations, and it always works this way, right? We've been doing this with regular problems where you're going to divide by this log. We're going to divide both sides by the log of 1.4, and that's going to equal your t value. Now, log of 10.55 divided by the log of 1.4, that's something that we need to do on a calculator. Make sure that you can do that comfortably on a calculator. You're really going to just want to type the whole thing in from left to right. You can use a regular scientific calculator to type the log of 1055. Make sure you close your parentheses there. Close those parentheses. divided by the log of 1.4. Same thing, make sure you close that parenthesis. So I can kind of type that in one step, and bingo, hit enter, and we get 7. Okay, now that's going to be the time, and the time in this problem is in hours. Go back and read carefully. Since the percent was in hours, the time is going to be in hours. Okay, now kids, this was what we would call kind of like a general percent change problem. Okay, something was changing by 40%. It wasn't specific to money, so we used the exponential model. But as we move ahead to this problem, we see very quickly that we are dealing with money. We're trying to figure out how long $5,000, it will take $5,000 to double if it's compounded continuously. Now, if you've not seen this formula, no panic. It's just the continuous compounding formula. It's A equals PE to the RT. So we can just start by writing it down. Well, what we want to understand here is that since I'm trying to figure out how long it's going to take my money to double, I need to come up with double. Well, double is going to be 10,000, of course, because I started with 5,000. So it's kind of like the problem's asking, how long is it going to take till I end up with a final value of 10,000? Well, the final value is always what ends up on the left side of the equal sign, so that my initial value can be filled in on the right side. Of course, for the letter P, but I still have my E. Now R is 4%, carefully changed to a decimal, so it's 0.04. And all of a sudden I have my equation kind of filled in. Now this looks like an equation that we were learning how to solve just last week. So we want to get to the business of doing inverse operations. I hope that you would start by dividing both sides by 5,000. Of course, when you divide 10,000 by 5,000, look, you end up with the number 2. Now, that number 2 is a special number because it basically came from or represents the idea of doubling. Okay, so it wouldn't have mattered if I was doubling $5,000 or if I was doubling $5. I would still end up with the number 2. Now, since I'm solving this thing for the exponent and it's got an e as a base, that's right, we're going to slap both sides with an ln. And when you do an ln, it actually cancels with the e. My exponent still comes tumbling down, but basically that's all I end up with. That is, on the right side of the equal sign, I just end up with 0.4t. The ln of 2, well, that's something that you can do on your calculator. Instead of me showing that on the calculator, I want to show you here that we can actually just write the ln of 2 and then finish by dividing both sides by 0.4. So if I do the ln of 2 divided by 0.4, that's kind of like taking 0.69 divided by 0.4. And I can do all that on the calculator without necessarily rounding my answer until I get to that last step where I end up with 17. Okay, so again, do the ln of 2. And then divide that by 0.4, and I get 17. 0.33 if we're going to round that to a couple decimal places. Now, is that months, years, hours? Okay, well, because my percentage, my 4% was APR, APR stands for annual. So annual is in years, 4% was in years, that means 17 years. For my time. Continuous compounding, A equals PE to the RT, and then get ready to slap both sides with an ln, a natural log. How about this problem? Looks like we're trying to invest $1,800 at 6% compounded monthly, but it's not asking me to find the time, it's actually asking me to find how much. How much money do I have after 5 years? Well, I'm going to be using the compounding interest formula, so at least I can start with that. But I want to be careful here when I start filling in values because it's actually the final value that I don't know. I don't know how much I'm going to have at the end of 5 years. So we're not filling anything in for A. Remember that your starting value, 1,800, is going to go in for P. Okay, that just stands for the starting value. Looks like I have an interest written as a decimal as 0.6. And then what's this idea of compounded monthly? Well, if something's compounded monthly, that means that there's going to be 12 compounds in a year. So I fill in the number 12 for the letter N. I'm going to fill in the number 5 for the letter T. Now, this looks a little complicated. There are a lot of numbers here, but if we just kind of do the order of operations, the first thing we really would need to do is just add your parentheses together. If you add your parentheses, 1 plus 0.6 divided by 12, we're just going to end up with 1005. I also can actually do my exponent and change that to 60. So again, I'm going to add my parentheses, kind of like simplify the base. I get 1005 with a calculator, and then I can actually multiply 12 and 5 to get 60. Now be careful, I don't want to get too log excited. I'm not going to slap both sides with a log. I'm not trying to solve for the exponent. Instead, I'm actually just going to continue to do the order of operations. And the next operation that needs to happen here would be to actually raise 1005 to the 60th power. And then you're going to multiply by 1800. Well, you know what? You can put that all in your calculator. You can basically take 1800 times 1005 to the 60th power. Again, I can actually type all that in one step, hit enter, and I end up with my final answer of 2427. Okay, so we want to do the order of operations, and our calculator can handle that. So if I put that in one step, I can end up with $2,427.93 at the end of 5 years. All right, one more problem. Looks like it's trying to figure out something with money, and we have this idea of being compounded semi-annually. Well, it doesn't say anything's being continuously compounded, so we're going to go back to our compounding interest formula. Again, it is the same formula. I'm going to write it down just so you know which one I'm using. Okay, but look carefully here. We're trying to find an interest rate. If we're trying to find the interest rate, that means that I don't know what the R value is for this problem. But I should know what everything else is. So what do we got here? A 10-year loan, a principal of $10,000. Again, principal just means what we start with. And we're going to try to borrow, there's actually a little bit of a typo here. We're actually going to try to borrow $13,000. Make sure you fix that on your paper. We're going to try to borrow $13,000. Okay, so that means that $13,000 is my final value. It's going to be filled in for A. Again, sorry about that little typo there. My principal, my starting amount is $10,000. Okay, so again, I always put my starting value in for P. 1 plus R. Remember, we discussed that we don't know what R is. Now, it says that it is been compounded semi-annually. Semi-annually means that N would equal 2, because basically you're compounding it twice in a year. So again, the letter N is always how many compounds in a year. We're going to change that. We're going to make that be the number 2 since it's semi-annual. But 10 years is my time, so I'll put the number 10 in for T. Okay. Now, this looks like a lot of fun, but I'm still not going to need to use a logarithm because I'm not looking for the exponent. In fact, if you do a little bit of simplifying here, you should realize that you can actually figure out the exponent. Okay, basically take 2 times 10 and we can end up with 20 for my exponent. So what do we got here? We kind of have an equation that we're solving for that R value that's in the inside. But you always work from the outside to the inside, so dividing by 10,000 is the next order of operations. And when I divide by 10,000, you can use a calculator if you want to, but it's basically just going to move the decimal place. It's going to move the decimal place 4 places, so we end up with 1.3439. I'm not going to round that because I already have all those decimals anyway. Well, the next step is to do something to get rid of 20. And again, don't use a log because I know what the exponent is. I'm not trying to solve for the exponent. So instead what I need to do is actually use a root. It's called the 20th root. I need to take the 20th root of both sides. That's going to be a calculator computation, so the big question is, how do I do that? Well, remember, you want to use that xroot command, and that xroot command is on your keyboard, and it has a little x in the spot of your root. So that means you want to type a 20 first, so that that 20 will get inserted in there as the 20th root of 1.3439. Well, we get this kind of the strange number 101488. I think we can round that a little bit right now, so we'll round it to 1015. But the 20s cancel, so I'm left with just 1 plus r over 2. And then all I got to do to finish this problem is subtract 1 from both sides and multiply both sides by 2. Of course, you want to do that in the right order, so subtract 1 first, and then multiply your answer by 2, and you end up with an r value of 0.30. What the heck does that represent? Remember, that's the decimal representation of 3%. So it looks like if this is going to happen, if you're going to start with $10,000 and end up needing to get interest that'll get you up to $13,000, that's going to happen at 3%. Well, kids, we've got 4 application problems that I went over, and now I'm going to ask you to do the 4 application problems on the other side. This will end up being your last assignment of the year, so do a great job with it. Finish up well. That's it.